Welcome, physics fans, to 101 Ways to Have Fun with a Whiteboard, Episode 1, Conservation of Momentum. Now imagine we have two balls travelling towards each other that are of different masses. So we have a large ball of large mass m1 and a small ball of mass m2. And they have opposite velocities. There's going to be a collision, crash. Now when the two balls hit each other, they put a force on the other ball. They're going to change the other one's velocity. There's going to be an acceleration. But Newton's third law says that if ball number 1 puts a force of magnitude F1 onto ball 2, then Newton's third law says there has to be an equal and opposite reaction. The force that the ball number 2 places back onto ball number 1 is of equal magnitude but opposite direction. So in this case, F1 is going to equal minus F2. The minus sign simply saying it's in the opposite direction, remembering that force is a vector. After the collision, they're going to bounce off each other. The velocity of each ball is going to change direction and probably magnitude as well. And so after the collision, they now have two new velocities, two final velocities, v1 and v2. Now, remembering Newton's second law, force equals mass times acceleration, we can now write F1 equals minus F2 in terms of the masses and the accelerations that each ball experience. So m1 times the acceleration of ball 1, so the change from this velocity in this direction to this velocity back in this direction, is equal to m2 times the acceleration that ball number 2 experiences. Again, they will be equal because we have a negative here, and acceleration is going to be negative as well, so they're both going to be the same answer. Now remember that acceleration is just the change, final velocity minus initial velocity over the period of time that the force is applied to an object, and there's a change in velocity. Now if we sub this relationship into this expression, we can now write this expression. So it's just this, but with acceleration, we simply expand it in terms of v1 and u1 for ball 1, and v2 and u2 for ball 2. Of course, the time for the collision is going to be the same for both, because it's the time it takes them to hit, those forces to be applied, to when they separate again. And of course, in most situations, that's going to be very small value. These collisions happen very quickly. Okay, now looking at this expression, we can see we have this time on both sides of the equation. So we can actually cancel that out. So cancelling from both sides, we can now write this expression, the mass of ball 1 times the change in velocity of ball 1 is equal to minus the mass of ball 2, again times the change in its velocity. Using the distributive law from maths, we can then expand the brackets. m1 v1 minus m1 u1 is equal to m2 v2, the negative of it, plus m2 u2. Now collecting terms for final initial velocities. So what I'm doing from this step to this step is I'm now rearranging, so all the final velocities are on this side of the equation and the initial velocities are on this side of the equation. What this says is, if we consider this term mv, what does that mean? Well, that's momentum. Now you may have heard the word momentum. You know, if you ran the ball forward in football with forward momentum, momentum really is a measurement of the stopping power, or the sort of force you have to use to stop something that's moving forward. Now, if you consider a truck travelling at 60 kilometres an hour, it takes a lot of force to stop that truck. You know, if that truck hits a wall, it's going to do a lot of damage. But if the same truck with the same mass, you know, someone releases the handbrake and it just inches forward at a very slow velocity, then it's not going to knock over the wall. It's not going to do damage to it. It's going to be far less force. It needs less stopping power. So really, you know, how easy it is to stop something depends both on its mass and its velocity. And this is where this concept of momentum is very useful. But what's really useful is we can use it in situations like this to actually predict what the final velocities will be. And it all comes from this last expression, that really the final momentum of both balls is equal to the sum of the initial momentum of the balls. Final momentum of the system is equal to the initial momentum of the system, or final momentum is conserved. Okay, the system doesn't lose momentum. You have to account for it all. A little bit like the conservation of energy that we've been using with potential, kinetic, when we're working out problems to do with mechanical energy. Now, this only occurs for certain types of collisions, elastic collisions. So imagine two pool balls or billiard balls hitting each other. Those two balls don't deform, they don't change shape. There's no energy or force going into changing their shape. All the force is pretty much going into changing the velocity of those two balls. Yes, you produce a bit of sound, which requires a bit of force and a bit of heat, but neglecting that, we call that an elastic collision. Conservation momentum works in those cases. If we have an inelastic collision, some of that force goes into changing, knocking the bricks out of the wall, changing the shape of the wall. Momentum may not be conserved. Okay, and this is a really useful concept in physics. And just to give you an idea of that, I'm going to show you a situation. So I'm just going to rub this out. Okay, let's consider a car crash. So we have the dashboard of a car. And we have a passenger. And Newton's first law, even if the passenger has a seatbelt, the neck is still going to move forward in a collision because there's no direct force on them. The head still keeps travelling at the same direction and speed, whereas the car, there's been a force applied to it, and so the dashboard is going to accelerate. Essentially what happens is the head will then strike the dashboard, and that'll do so with a pretty big force, and that can result in severe injury or in fact death, depending really on the momentum of the car in the first place. Now, this is a very sudden acceleration that the head experiences. It's only when the head actually strikes the dashboard it changes its velocity. So it's acceleration like that. The time it takes for my fist to actually make contact with the wall, that's the time period of that acceleration. Now let's look at Newton's second law again. Force equals mass times acceleration. The bigger the acceleration, the bigger the force. But remember, let's rewrite it in terms of changes in velocity. So just like we did before, the final velocity of the head minus the initial over the time period it takes for that collision. Of course, the initial velocity is going to be the speed the car is travelling and the head was travelling, so let's say 60 kilometres an hour. The final, when it strikes the dashboard, is going to come to rest with respect to the dashboard, so 0. So it's a big change in velocity, and of course, as we just said, if it directly strikes the headboard, that time period is very, very small. And we can see that because it is the denominator, the larger the number, what's that going to do to the force? It's going to reduce it. The smaller, which is what happens to this type of collision, is going to be a really big force. But this gives us a clue how we can protect the passenger. If this becomes large, dividing by a larger number produces a smaller force. And so this is where the idea of an airbag comes in. In a collision, the airbag inflates. Now the airbag's not there to make the dashboard somehow softer or cushionier. It's not to make that final blow somehow softer. I mean, you're still producing that acceleration. It's not going to work like that. But what it is going to do is it's going to slow down that acceleration. It's going to slow down delta t. Instead of hitting straight away like that, it's going to hit the airbag and then slowly change velocity. This is still going to have the same change in momentum, but the time is going to take a lot longer for it to occur. And so the force that the head hits the dashboard with will be significantly lower, and there's a very good chance the passenger will have less injuries, and will survive the crash. Now, this change in momentum, because we expand this out, really is mv minus mu again. We can write, give it a symbol, delta p, p for momentum. Yes, I know momentum doesn't start with a p. Simply equals the final momentum minus the initial momentum. And so we can rewrite a new expression for force now, that force equals this change in momentum over change in time. Or of course we can write change in momentum equals the force that's applied to do it over the time that that force is applied. F delta t. Momentum, of course, what is it measured in? Well, it's mass and velocity. So delta P equals kilograms is what we measure mass in SI units. What do we measure velocity in? Meters per second. So dot or times meters per second. Okay, so that's conservation of momentum. In a closed system where we have elastic collision, the final momentum of the system has to equal the initial total momentum of the system. So the momentum of both parties, of course. And we can relate that back to force, in that force really is the change in momentum of an object divided by the time it took for that change to occur. Okay, enjoy that. That is episode 1 of 101 Ways to Have Fun with a Whiteboard during lockdown. Can't wait for episode 2. Good night.